Welcome back again. I'm Dr. Bettina Heinz, who will teach you some more about chemistry again. Today we will continue with matter part 2 because we want to show you a few lab videos. And I will tell you a little bit about the important technique of chromatography that allows us to separate mixtures into their constituent components. Remember, matter is usually very heterogeneous. Most matter around us consists of mixtures, and the chemist's job is to isolate the individual compounds from another. So here we have an overview of how chromatography, or the separation of compounds, occurs all around us. This house, for instance, has experienced a lot of rain, and all the muddy components are creeping up the stucco of the house. So this is a very crude type of chromatography, not very valuable for analytical purposes. But chemists or scientists have noticed this phenomenon and then worked it out into a real important technique. And now things are so refined that we can do various types of chromatography using different types of materials or driving chemicals that help to separate the components into different arrays. So here we have the most early type of chromatography, the paper chromatography. Today we have it converted into all kinds of surfaces or adsorbing materials like silica, gel, or silicon dioxide, aluminum oxide, cellulose are some very common ones. Paper has been converted into a so-called thin layer chromatography technique. They also had a thick layer chromatography technique. Nowadays we can purchase all the materials out of a catalog in all different kinds of sizes. This example here would be an ascending type of chromatography. That means according to capillary forces, the components are driven up by the effluent or the eluting liquids, the mixture of certain liquids that separate the components according to their different properties, polarity, adsorbing or adhesive type of conditions, how well they are attracted to the surface, how well they are attracted to the solvent systems. It's always a contest. What am I attracted more to? And that allows the fine resolution of the different components of a mixture. Here we have an example of a column chromatography setup where we have a descending type of separation. We put our substance on top of a column that is filled with the adsorbing material, which can also be silica gel, aluminum oxide, or cellulose, or modern, especially formulated powders that will have to be gelled with some solvent and then filled into the column. We always have to keep everything wet, so the mixture will be driven by a solvent system, just like with the other technique, down through the column, and we can isolate the different fractions as they come out from the bottom. So this is also a preparatory way of separating the components because we can do further analysis of the fractions or the cuts or whatever we may call them. We also have automatic fraction collectors that even allow us to isolate very fine or very small amounts. Normally chemicals are not always colored, so we have usually a UV ultraviolet detector that will graph things out for us so we know which component is which. The RF factor is very important here, which we call the retention factor, which means how well is a component attracted to the fluid system, the effluent system, or the liquid mixture that drives the chemicals. Here I have a crude little sketch of a gas chromatographic column which uses not a liquid driving force but a gas, which is helium. But the column also contains a solid through which the components are driven by the gas, and they come out at different times depending on the retention factor, and we have a nice array of spectral peaks that can be correlated to whatever component we are interested in. in analyzing. Now it's time to see some lab videos, and we have 3 to show you today. So that's first the distillation technique for separation, and then I'll be addressing you again, and then we'll introduce extraction, and then finally filtration. So enjoy. Hello, we are now ready to do some experimentation here in our lab, which is not the most modern at the time, but remember the old chemists also worked in more historical conditions. So we have here a setup which we call the distillation apparatus. We have a heat source. This is a very modern heating mantle. We have here our distilling flask, a round bottom flask, already with a side arm that connects to our condenser. The condenser is the one that will condense the evaporated liquid molecules back into their liquid form or physical state, and we will collect the distillate, the recondensed liquid, here in the receiving flask. So it's going to be here on this end of the setup. Now, distillation is a separation technique used to separate solvents or liquids from a solute, dissolved substance that is found in a solution, for instance, which we can't separate otherwise. But by driving off the solvent via distillation, via heating it and boiling it and evaporating it and recondensing it, we can get the mixture separated into its components. So in our case, we have potassium permanganate, some purple crystals that make a wonderful magenta colored solutions. So I'm going to add a little bit more water. It's very concentrated, but we did that so we can see the color. And when we do the separation procedure, we have to put a thermometer in here and seal off the system. And we need to be able to cool the evaporating liquid by condensing it. And we need what we call a cooling mantle. And this is done by water from the faucet. So the water should come in from the bottom, which is done wrong here. So we better turn it around. So we see here a condenser which is cooled by an outside mantle of water. The internal column is not in contact with the outside column. That is very important because we don't want to mix anything. So a condenser has a cooling mantle with faucet water, and the vapors that are formed will then go through this condenser, and because they come in contact, the fast molecules come in contact with a coolant liquid, which is water in the outside mantle coming from the faucet, and then they will be slowed down, and then they will go back into their liquid physical state. And later on, when this process is going on for a few minutes, we will see little droplets forming, and the dripping will be then observed into the receiving flask. Now this is a beaker, so we would call this a receiving beaker. This is our heating mantle, which we can regulate. We can regulate the heat by this control box. And the best thing is not to heat it too abruptly. We can use the margin 3 here. And this is the thermometer, which will reach, should reach down a little bit more, but it will tell us the heat of the vapor molecules. And since we have water as a solvent here, guess what type of temperature we would observe once we have a constant flux of the vapor molecules here. It would be steady at 100 degrees. As long as we have a state change, the temperature remains constant. So I could even get a cup of coffee in the meantime because the condensation will be at a steady state. So now the temperature is 45 degrees centigrade, and we have a little ways to go. We will start noticing that the mixture here in the distilling flask will start bubbling and boiling, and we will see condensation building up. So that'll be very interesting to observe later on. Now, what do you expect will be the color of the distillate? The fraction that we will collect here on the other end of the distillation apparatus. Well, naturally, since we have a pure separation, we should obtain pure H2O, pure water. And if I am daring, I could drink it later on. Now, with the permanganate, it's not so bad either, because permanganate is a disinfecting crystal or substance. It's a KMNO4, the formula. It's a oxidation agent, so it can disinfect. It used to be used as a gargling solution, but it's highly concentrated. So it still keeps its color even in the most dilute solutions. Now remember, a solution is solute, the dissolved substance, with a solvent. Together they build a solution. Now, as I already mentioned, we can also separate two liquids of different boiling points. But they have to be miscible. That means they have to mix with each other, make a pure solution with each other, so that you don't see any phase difference. We have this technique used every day in the petroleum industry, where all the fractions of the natural gas, natural petroleum are separated into their components, into diesel, into light benzene, into all the different components, including anthracite, or the material that we pave the roads with. So we can do that by change in their boiling behavior. But they're all miscible substances, so they're all hydrophobic liquids that very well mix with each other. Here we have hydrophilic situations, so hydrophilic solvents would mix with each other, like alcohol and water, so you could separate them by distillation. Although I must caution you, some liquids make what we call azeotropic mixtures. That means constant boiling mixtures, so they can't be separated at a certain point, at a certain concentration or molar ratio. So that's another story. That's for another chemistry class. But for our situation, this is a very good technique with which we can separate things. In the old days, they used this in the moonshine era, where alcohol was illegal. People had these setups in their backyards distilling alcohol. So we will leave this apparatus for a while and then check on it again to see what kind of progress it has made. We have to make sure, yeah, see, I can see already the condensation building up. So we're getting ready to roll. The temperature went down a little bit, so maybe I should heat it up a bit more. And then once it is 100 degrees, we'll check on this apparatus again. Yes, we're back again checking the distillation apparatus. And as you can see, the solution in the distilling flask is really vigorously boiling. So water is moving out. Going up here, sitting on the tip of the thermometer as a condensation droplet a little bit. We can look at the thermometer. It is 100 degrees, so that means the boiling point has been reached of the distilling solvent, which is H2O, which is water. So you see, distillation is always also a technique in determining the boiling point of a liquid. And then when we move here through the condenser, you see the water here really sliding down beautifully and then dripping into the receiving flask. And look at the color of the distillate. It is colorless, so that means it is pure water. And we could wait till everything is distilled off. We should never distill absolutely to dryness, because remember, the other component of the mixture is solid. So we will see the crystals forming if we would really boil off the liquid completely. So we don't do it all the way. What we could have added also to prevent sort of intensive type of boiling, the so-called boiling stones, which ensure a smooth boiling. Now here it's not a big problem, but some liquids, they shoot up because they're so violently boiling. And then these boiling stones, they can be little glass beads or little volcanic pieces of rock that absorb some of the air that produces this violent boiling. So we can leave this experiment now, and I hope you have understood everything about it. And it's a very straightforward experiment and very valuable tool for chemists. Well, I hope you enjoyed that. We have another interesting video to show you, another important separation technique, which we call extraction. And I hope you are also entertained by this video. Hello, welcome back to our lab. We will discuss another interesting separation technique today, and that is called extraction. That means you literally extract a chemical from one solvent and move it into another. This is a very valuable technique. It's used a lot in organic chemistry with separatory funnels, especially in isolating natural products from their sources, the plant material. But here we have a simple way of demonstrating this technique. We are going to use iodine solution, an aqueous iodine solution, meaning iodine dissolved in water, which makes, I'm going to pour it directly here into the big flask. And you see that it makes a beautiful amber-colored solution. So it's in a polar environment because water is a very polar solvent. But it's not completely happy here. It would be more happy in a non-polar solvent, an organic solvent such as hexane, carbon tetrachloride, benzene, chloroform, etc., etc. So these chemicals, these two solvent systems are not miscible with each other. So they make an interface. So they don't make a pure solution. You can see the little barrier where one liquid sits on top of the other. We call that a phase difference. And I'm going to add now hexane. Smells very organic. And I'm going to pour it onto this aqueous iodine solution already. I better stop this because the vapors are not very healthy. So we see here, nothing happened much yet, but you definitely see the beautiful interface. Now, which you think is the less dense liquid? Well, obviously the one that is on top, and that would be hexane. So hexane has obviously a lower density than water. Now, that's a good proof. Now, the iodine will start recognizing that liquid, and you can see a very, very faint pink coloration of the top layer. That means the iodine molecules are already migrating up into that portion of our test tube here. But I can help them along by agitating the solution, the two components, by shaking. And look what's happening. The top layer is getting into a nice pink coloration, and the bottom amber-colored liquid is getting paler or fainter. Well, we can understand that because the iodine is moving away. It's moving out of the water into the organic phase. And if I shake it more vigorously, you see the bottom is practically colorless. So all the iodine is now where it wants to be in the non-aqueous part of the surroundings. So all the iodine molecules moved into the top layer. Now I could use this further and use what we call a separatory funnel and isolate or pipette off the top layer here, and then let the solvent evaporate, and then I would have the iodine crystals back in my crystalline solid form. So that is an extraction method, the extraction method of isolating chemicals by moving them from one solvent into another. Now let's imagine iodine was with many other chemicals together in a heterogeneous or heterogeneous solution. Then I could selectively isolate iodine from its neighbors. And that is a purification technique. So isolation, extraction techniques, separation techniques, etc., are valuable methods to isolate certain chemicals and separate them from others. And in chemistry, that's what we usually want to do. We want to purify chemicals. We want to isolate them and then do research with them and study them and so forth. So most chemicals, as you remember, are in mixtures. And Extraction is a valuable technique, as you have readily seen by my demonstration. In organic chemistry, this is used a lot, but we're not studying organic chemistry in this course. That would be interesting for a future course. Remember, chemistry is also the study of techniques. So we have one last one, and that is the technique of filtration. So I hope you enjoy this rather short one. Hi, we're back in the lab, and we will do a separation technique today, which is called filtration. And filtration uses a funnel, a filter paper, and a flask to collect the filtrate. Now, what is filtration? We will separate a solid from its solvent. That means that it's a bad solvent because it's not able to dissolve it anymore. But sometimes we get a solid formation in a chemical reaction, and it needs to be separated out. And that is what we will demonstrate. We will take lead nitrate solution, which, as you can see, is a clear solution. And we will add chloride ions coming from hydrochloric acid. And we will see that instantly a precipitate forms. You see the cloudy white solution here. It is opaque, that means not transparent anymore. And you see it already settles to the bottom very readily. But this is of no use to us. We need to separate it out. So I use my funnel that has to, of course, be equipped with a piece of filter paper, which cannot just be put on top here or stuffed in here like that, like some foolish students might do. We will have to fold it carefully once, and then again. And then we tear off a little corner so that the filter paper will stick to the funnel glass better. In this case, we have a plastic funnel. And then we put it in our funnel rack. We can wet it a little bit with water to make it stick better to the sides. And then we have to swirl the solution and use a glass rod as a guideline for the liquid to flow over neatly into the filter. And then you see the filtrate dripping through into the receiving vessel, which is also an Erlenmeyer flask, and it should be completely clear. If it's not clear, you have to filter it again. So you have to be very careful in filling the filter paper with this solution. And you wait till it goes down a bit, and then you pour a little bit over again. And on until the whole material is separated out. The solid will remain behind in the filter paper, and it is called the residue. The clear liquid that comes through is called the filtrate. So the filtrate will contain the nitrate ions coming from the lead nitrate solution and hydrogen ions, or speak hydronium ions, coming from the acid. The lead combined with the chloride ions to make PbCl2, which is a substance that is not soluble in water. Its solubility is very, very minute. This is, of course, to our benefit, because then we can apply the filtration separation technique. And I'm going to take a look and see how dry the residue is. I'm going to cheat a little bit so you can see it. You can see the crystals here being held back by the filter paper. The solution or the filtrate should be clear, and it is, so I did a good job. And then when everything is done, you rinse it a bit with water or acetone, and then the process is done. That, ladies and gentlemen, is filtration. In order to wrap up today's episode, we dealt a lot with the laboratory techniques. I want to show you, last not least, also the importance of the chemical equation that is a symbol for a chemical change in the form of reactants yielding certain products. You see here in this slide a student preparing an experiment of burning magnesium. Remember, we saw that in an early lab video before. This is used to determine what we call the empirical formula or the lowest molar ratio formula. You see here the reaction is magnesium plus oxygen gives magnesium oxide. That's what we call an addition, combination, or synthesis reaction. According to Lavoisier, we have the conservation law of mass. That means the matter is not produced or destroyed during a chemical change. The atoms just break up their old bonds and create new bonds, as also Dalton formulated. So you see the student is having some magnesium ribbon that he will burn in a crucible to have the magnesium react with the oxygen of the environment, the atmosphere rather, and to make a product. You see here in the overhead that we have a crucible on top of a ring stand, and we heat up a certain pre-weighed amount of magnesium, put it in the crucible, and then let it react with the air. And air, of course, contains oxygen and nitrogen, so we get actually two products at first, the magnesium oxide and magnesium nitride that I have to correct here, so it's an N. And the magnesium nitrate can be easily destroyed by adding water temporarily. That will break down into magnesium hydroxide that is burned off as magnesium oxide. And you see that we get an equation that just describes this chemical change. And here we see how the reaction occurs in the crucible. And then in the end, you get sort of an ash-like powder that can be weighed. And with this, you can do some quantitative and qualitative analysis. And that will conclude our program today. Thank you.